Hello folks, today we will discuss LeetCode question number 2421, number of good paths. So in this question we have been given a tree and we have to find number of good paths in this tree. Now what does a good path mean? It it basically means that the starting node and the ending node of that node have the same value, and all the nodes that come in between the path should have a value less than or equal to the terminal nodes. For example, in this example, total number of paths are 6. Why? Because each one of these nodes can be a path, and one good path can be this 1024. Why? Because the terminal nodes have the value 3, they have the same values, and all the nodes between them are 1 2, so they have the value less than the terminal nodes, right? And we have to find the count of all such paths. Okay, how can we do this, right? How can we approach this problem? There is a very beautiful solution to this. What we can do is we can construct the tree in the increasing order of the values. Okay, let's try to understand through a diagram. Let's say I have a tree here. Okay, let's say this is my tree. Okay, and these are the values like 5 1 4 3, and let's say this has the value 4 and 1 1 1. Okay, let's say this is my tree. Okay, now what can I do is uh, I can first um, I I can first consider these nodes like the 1 1 and 1. Okay, because they have the least value, and then check how many paths can I get here, right? How many paths can I get here, right? So for that, what I need to do is first I will check how many connected components are here, right? These 3 points are not connected here if I only consider these nodes which are in the circle, right? So how many paths can I get? 1 2 3 and 4. Okay, yep, we have accounted for. Now let's take another set of increasing value. Let's now take 3 also. Okay, uh, I have also taken 3. Now I will see how many connected components are here. Okay, they are like 1 2 3 4 5. Okay, 1 2 3 4 and 5, right? But now we don't have any connected path here also. Okay, so I will just simply add one because the newly added value has only one component here, so it will be counted as one. Okay, now we will move on to the next, right? It will be 1 3 and then comes 4. Okay, now I have come to 4. Now as you can observe, for this 4, how many paths can I get, right? I can get this, and I can get this, right? I cannot get here, right? Because this is the end node. Okay, so how many paths can I get? I will check, like if if I'm if I am also taking these, this entire thing will become one component. Okay, because all the nodes here are connected now, right? So as all of these paths are connected, what I will do is I will just simply take this 4 and I will see how many paths can I get from here. Okay, number of paths that I can get is 1 2 and 3. So I will add 3. Next I will append 5. I will append this 5, and now we are considering the entire tree. Now because of just 5, how many paths I am getting? It's simply 1, because I am not getting any other node that ends with 5, so I can connect them together, right? So it's 1. Now the answer comes out to be 4 plus 9, right? This is how it's gonna be done. Let's take one more example to clearly solidify our understanding for this approach. Okay, let's say I have this tree. Okay, Now it has value like 3 1 3, okay, 3 3 3 2, and here it also come as like, let's say 2. Okay, this is our tree. Okay, and we have we have values like 1 2 and 3. We have these unique values that we can use for making the paths. Okay, great. Let's start with 1. I included this one in my tree first, in my resultant tree. Okay, this is my resultant tree. Let me make it here. Okay, this is my resultant tree. It has value 1. Okay, great. How many paths I can make from here? 1 only, which is this single node. Okay, so I will add 1. Now I will move ahead. I will include 2 also. Okay, now if I want to include this 2, okay, we have done, right? Now I have this 2 also, so I will connect. Okay, plus one more thing that needs to be addressed here is that if I am including these nodes, I will only make connections here but not here. Why? Because one has been already included before. So if I'm including this 2 also, I will not include these 3 because they will come afterwards and they will not contribute to the path at the current level. Okay, now I have added this 2 also. Okay, now in this component, how many paths can I get with paths ending at 2? How many can I get? 1 2 and 3. Okay, so I will add 3. Okay, great. Now I will include this 3 also. Let's do it then. If I'm including this 3, we get this entire tree here like this. Okay, so yep, we have done. Right now this whole tree will be considered for counting. Okay, as you can see here, we have total number of 3s we have is 5. Okay, total number of 3s we have here is 5, and the number of unique paths that we can make from this 5 3s will be NCR, right? We will use combinatorics here. Why NCR? Why NCR? Because out of this 5 ends, we will only choose 2. For any unique path, we only need to choose any 2 of them, right? Let's say I want to choose this and this, that will give me a unique path, right? This and this, it will give me a unique path. Okay, like this and this will also give me a unique path like this. Okay, so if I want to pick 2 out of 5, that will be in the mathematical terms NC5, 5C2. Okay, so it will give me 5C2, which also is 5 into 5 minus 1 by 2. It's very simple. Okay, so I will add 5C2 here, but here we also need to take into consideration the paths that are only consisting of single node, right? That will be these 2 3 4 5, because here we are not taking into account that. Okay, so I will just do plus 5 here. Okay, so this is my answer. It is 1 plus 3 plus 5 into 4 by 2. It becomes 2 10. 1 plus 3 plus 10 plus 5, that becomes 14 19. So the answer is 19 here. Okay, now I have explained the approach, but now how to implement this? Okay, how can I implement this? So this is the implementation part. Now what can I do is, I will first keep track of all the values here. Okay, let's say for one, what nodes I am getting. Okay, like if the nodes are indexed like this, right? 0, this is 0, this is 1, 2, 3, 4, 5, 6, right? If nodes are numbered like this, here in this tree, 1 will be only and only 1. Okay, this will only be 1. Okay, now for 2, I am getting 0 comma 4. Okay, now for 3 we have 2 comma 3 comma 5 comma 6 and 7. Okay, we have this can be done using a map, a hash map. Okay, great. Now what's next? Okay, first of all, what we have to do is we have to include the nodes one by one based on the values, based on the increasing order of the values. Okay, so first I have included this one, then I have included this 2. After that I have included all these values in the end, right? So we are going in the in increasing order of the values. Okay, that can be done using a union. Okay, how? First what I will do is I will make a graph where I have a directed I have a directed edge from the increasing value to the decreasing value. Okay, like here the value is 2, right? So this will be one of the edges. Okay, and this will be one of the edges, like this, right? So if I'm adding 2 in the tree, I will connect it to this one, and all the other values that are connected, that are adjacent to the node but have the value less than 2, right? So what I will do is I will make a graph like this. Is not like here, 1 is not connected to any node, 2 is connected to 1, right? All the ones, all the 2s are connected to all the ones if they have a common edge. Same case for 3 is connected to all the common ones and all the common 2s. Okay, as simple. And then, right, if I am at 1, I will add this one. Now if I am at 2, okay, what I will do is I will connect them using union find. Okay, I will connect all these using union find, and then count how many 2s are there, which will give me the number of paths. It's that simple. Okay, now let's move on to the implementation to understand this approach even better. Okay, first let's write the code for implementing the union find. Also, one more thing, if you don't know how union find works, what you can do is just simply consider the code for union find as a black box, right? Treat it as a black box that does some magic and connects any two nodes and keeps track of the parent of that group, right? You can learn union find from any source, right? But here you can treat it as a black box if you don't know it already. This is the function to find the parent. Okay, these are the vectors for parents. Let's define the size for these. Right, here we have n-1 edges, right? So the number of nodes will be edges. Okay, great. Now initially I have said all the nodes is parents to themselves. And the size will be 1. Okay, now let's make Now integer a will be I and b will be 1. Okay, if 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 value of a is more than b, a will be connected to b, right? Okay, done. Now let's begin the search. Okay, first all we have to make this hash map also, right? This. Okay, let's make it then. Nodes with value. Okay, we can add it here only. And also for b. Yep, we have done it. Okay, now I will systematically move from the lowest value to the highest value, and I will just simply make connections across the nodes. Okay, let's see how I'm doing this. Yep, we have done. Okay, now for all the nodes in the node list, right? For each node, right here, let's say I am traversing for the value 3. Okay, for each 3 and for all the connected values, I will just connect them, right? Like for this 3, I will connect here, 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 and here. Okay, connect. I will implement these later. Okay, let's not focus on them now. Let's focus on the algorithm first. Connect. Okay, we have done it. Okay, we have made the connections now. Now, but also one more edge case can be happening, which is that there are different parts of the trees that are connected to each other, but each of them have a different value, have a different amount of nodes of that current value, right? Like if I am having 3 2 3, okay, and 3 3 3 and 1, like this. Okay, in between I have this 4. Okay, like this. Okay, if I am at 3, this 4 would have not been added, so we have these two components, right? So for this, number of good paths will be 2c2 plus 2 plus 3c2 plus 3. Okay, for all of the values. Now how can I make this? Okay, first of all we will connect all of these. Okay, let's say we have these amount of like groups, 3 and 3, let's say like this. Okay, we have these groups currently. Here will be value and dot equals to value. Okay, we have these groups. Okay, now here we can have 3c2 plus 3. Okay, so let's add also. What I will do is, after making all the connection, I will count for each parent how many nodes are there, right? For here, let's say the parent is p1, so for p1 we have 3 3s, and here for parent p2, let's we have two 3s, and here we have 3 3s. Okay, for each we will calculate the sum. Okay, great. We have made the necessary connections, and let's say count for each group. This will go inside also, of course. For auto, this for this 3 we have this. Okay, for auto node in we want this. Okay, for auto node in node list, count for each group, find node. Okay, yeah. So what I'm doing is, here this function will give us the parent for that node, and I will count the frequency, like for how many nodes are there for each parent, right? I will keep the account for this. Okay, and let's put an integer. Now I will iterate through all the groups. Answer plus equal to size into size minus 1 by 2 plus size, right? This exact thing I am doing here, right? This will be 3 into 3 minus 1 by 2 plus 3. So same thing I am doing here. Okay, great. We have done this, and in the end I will return the answer. But before returning them, I need to implement these values also, right? So let's do it quickly here. Done. Now we have to implement connect. Let's say I want to connect A to B. Okay, let's initially fetch the parent of A and then parent of B. If both of them equals, which means that these two values are already connected. Else I will find the size of the first parent. If size of parent A is more than equal to size of parent B, which means that B will be contained inside A. This is path compression with union find. Okay, so parent B will be parent A. Parent A and size of parent of PB will be parent A. Okay, done. And else I will do just exact reverse. Yep, we have implemented this also. Let's submit and maybe check for any errors or any wrong answers. Is a parent. Okay, this will be parent. Okay, great. By where I am using parents, it is line number 24. Oh, okay. Okay, I am getting the wrong answers. Okay, fine. Let's debug where I am making a mistake. Okay. Oh, dot value there, dot pushback. Okay, this is correct. This is also correct. Connect node comma child. Okay, let's count for each group. Okay, this is also looking good to me. Count for each group. Okay, I am getting a wrong answer. Let's try to debug where I am getting a wrong answer. Okay, where I am making some mistake. Okay, looks good to me. From node list, right? If I am at node list, okay. Okay. This might be problematic for me. This gives me 0. Okay, why I am getting a 0 here, but here I am getting a 7. Okay, let's see 1 size into size minus 1 by 2. Oh, okay, maybe no, it should work, right? If the size is 1, I should get 0. Find node. Okay, so here nodes this is being empty. Okay. Let's see our previous submission and check if I'm making any blunder here. Let's see. This is my previous submission that got accepted. Let's see what blunder I'm making. Okay. Oh, maybe I'm pushing these values again and again. Okay, this can happen. So I can also make it as a set. This might fix. Yep, it fixed things for here, but also then it will not cover the case where there are no edges, right? So we will revert this and to make this hash map we made a mistake, right? So what I'll do is simply I don't need this now. Okay. Okay, great. And now we don't need this. Let's see how it comes now. Yep, we got accepted all of the three cases. Let's try to submit this and hope for the best. After that we'll summarize the entire approach once again. Memory limit accepted. Okay, so maybe I'm making some mistakes somewhere, but let's see how. Okay, I am getting a memory limit exceeded. Vector graph. Okay, this looks okay to me. This also look okay. Why I am doing this? Maybe there was some extra code that got written for some reason. Yep, let's submit it now. This got written again here, right? Yep, it got accepted. Now let's try to understand the approach from the start till the end. Okay, suppose I have a graph. Okay, let's say I have a graph for okay, suppose I have a graph like this and this like this. Okay, and the values are as follows. Like this is the value 4, these are value 2 2 and 3 3 3. Okay, and here it's also 3 3 3. Okay, great. Now let's try to understand. Let's try to understand now. Okay, first we have the value for 2. Okay, and the indices are as follows. Like let's say this has 0 1 2 3 4 5 6 7 and 8. These are the indices. Okay, now the hash map looks like this. Okay, 2 we have 1 comma 2, and for 3 we have 3 4 5 6 7 and 8. Okay, nice. Now for 4 only 0. Okay, now this is my hash map. Now what I will do is, okay, observe carefully. I will iterate in this direction, okay, and I will keep on adding the nodes. Okay, first let's add the nodes with value 2. Okay, that will be like this. First node this and node this. Okay, right, these two nodes I have added. Let's put the color correct. Okay, these have the value 2 2 and the indices are 1 and 2. Okay, now observing this graph, how many components we have two components. Okay, that can be known using union find. So if you don't know the approach already for union find, please consider that as a black box here, and just think that it just works magically. Okay, so here we have this and this. Now how many paths can be make here, right? It will be only and only two. One using this as a single node and the other with this. Okay, great. Nice. Now I will add the 3. Okay, now if I'm adding 3, what will happen is I will be iterating through all these values and I will connect these nodes like this, using the connect function that I made in the code, right? So that is 3. Okay, and now if you can see here in the graph, we have two components here. Okay, and taking 3 as the end point, how many paths can be created here? How many paths can be created here? That will be 3c2 plus 3. Okay, so that will be 3c2 plus 3. Same case goes here, plus 3c2 plus 3. Okay, for this now. Okay, great. We have now also tackled 3. Now if I'm taking 4, okay, now if I take 4, 4 will come here and will wait. If I take 4, that is 4 here, and will take like this, completing the tree and making tree as the one big component here. Okay, now let's just imagine we had 4 here also, like here also. Okay, let's say I had 4 here also, right? So that would have placed here. Okay, here and here. Okay, like this, 4 4 4 4. Okay, now how many paths would have gotten from 4? Will be 1 2 3 4 5, would be 5c2 plus 5. Okay, I can take any of these two nodes and create a path. Let's make an example for it. Like let's say I take this and this. Okay, so there is only one path because this is a tree, so any two nodes will have exactly one path. Okay, I can take this, I can take this, I can take this, I can take even this, or maybe I want this, I want even this, right? All of these can be done into 5c2 ways. This is like combinatorics, right? It's not very tough, and it boils down to 5 into 5 minus 1 by 2 plus 5, like this. Okay, so here I can make any type of path like this, or even like this. Okay, like this. So this is how the approach works, right? Now let's discuss the time complexity for it. Okay, so here time complexity is simply big O of n, because I am iterating through each and every node exactly once. Like if I am at 3, I will iterate through them exactly once, or maybe max to max twice. Okay, also I will go to their parent nodes for each node. That's also linear. Okay, so the time complexity here will be big of n. Okay, also the space complexity, speaking of, this is like linear, this is also linear, linear, right? So space complexity is also linear. Let's check, right? It's linear. Space also should be linear. Yep, so this was pretty much it. That was our code. I hope you like the approach, and please drop down any comments you might have regarding the approach. Okay, thank you.